In this section, we will take a closer look at how we evaluate machine learning models. We have already seen in the big picture section why evaluation matters and what can go wrong. Now we will get precise, introducing the formal definition of what we are actually trying to estimate, understanding the sources of error in our estimates, and covering the main validation schemes you will encounter in practice. Let us start by grounding the discussion in the notation we introduced in the first module of this course. Recall that the inducer I maps a dataset D and a configuration lambda to a model F. What we care about now is not how well this model F performs on the data it was trained on. What we actually care about is the generalization risk, the expected loss on new unseen data drawn from the same distribution P that generated our training data in the first place. We write this as Rgen of F, this expectation of the loss over all possible data points under P. The fundamental problem is that computing the generalization risk exactly requires knowledge of P, the true data generating process, which we never have. All we have is a finite sample D of n data points. Everything in this section is about how to use that finite sample as wisely as possible to estimate the generalization risk Rgen. Before we can talk about estimating generalization performance, we need to be precise about what quantity we are trying to estimate. This is called the estimand. Simply saying we want to estimate the generalization error is not precise enough, because generalization performance is not a fixed property of the configuration lambda in isolation. It also depends on how much data the inducer gets to train on. The proper definition is as follows. So fix a configuration lambda and a training sample size n. The estimand is then expected generalization risk of the model when induced from an IID sample of size n from P. We write this as the risk we had beforehand of the configuration, but now with an upper index n indicating the sample size, where then the expectation is taken over all possible training sets of that size. The E here is the expected value over all possible training sets of size n that could be drawn from P. Intuitively, if you were to repeat the entire process infinitely many times, each time drawing a fresh training set of size n, inducing a model and measuring its generalization risk, then this risk is the average result. Two consequences of this definition are worth highlighting. First, the training sample size n is explicitly part of what we are trying to estimate. A model trained on 500 data points will generalize differently than the same model type trained on 5,000. So the quantity we report is always implicitly tied to the amount of training data used. Second, we need to estimate this quantity using held out data from the same distribution P. Data the model has never seen during training. Any estimator that we compute from finite data has two fundamental sources of error: bias and variance. Understanding these is essential for choosing the right validation scheme. Bias is the systematic deviation of our estimator from the true quantity. A biased estimator consistently over or underestimates the true generalization risk. A concrete example: if the validation scheme trains on fewer than n data points, for instance, because we reserve a large portion of the data for testing, then the models we evaluate are weaker than the model we could actually deploy, and our estimate reflects a worse performance than the true generalization risk. This is a bias in the risk estimate. Variance, on the other hand, is how much the estimate fluctuates across different realizations of the data split. A high variance estimator gives very different answers depending on which particular samples end up in the training set versus the test set. A single small test set is the canonical example of a high variance estimator. A handful of easy or hard examples can swing the results substantially. These two sources of error are in tension with each other, and this tension is the central trade-off in choosing a validation scheme. If we make the training set larger, closer to the full dataset, we reduce bias because the induced model is closer to the one we would actually deploy. But a larger training set means a smaller test set, which increases variance. Conversely, averaging over more repetitions reduces variance, but at a higher computational cost. Every validation scheme we will discuss makes a different choice along this trade-off. The simplest validation scheme is holdout validation. We split the dataset once into a training dataset dtrain of size n and a test dataset dtest with the remaining samples. We induce the model on the training dataset, evaluate its empirical risk on the test dataset, and use that as our estimate. The appeal of holdout is its simplicity and speed. It requires training exactly one model. For very large datasets where a single task set is already large enough to yield a reliable estimate, it is also the natural choice. The weakness is variance. A single split is one draw from many possible worlds. So if the split happens to put many difficult examples into the test set, the estimate will be pessimistic. If it puts easy examples there, it will be optimistic. There is no way to know which world you are in from a single split alone, because you cannot observe this variance. This is the fundamental limitation of holdout validation, and it motivates the methods that follow. K-fold cross-validation addresses the variance problem by reusing the data more carefully. We partition the full dataset into k disjoint folds of a roughly equal size. For each fold j then, we induce a model on all data except fold j and evaluate it on the remaining fold. We repeat this for every fold and average the k resulting estimates. The key property is that every data point appears in the test set exactly once and in the training set exactly k-1 times. No data is wasted, and the averaging over k folds substantially reduces variance compared to a single holdout split. A special case worth mentioning is leave one out cross-validation, where k equals n. Each fold contains then exactly one data point. This is maximally data efficient, but also maximally expensive, and in practice it is only used for very small data sets. On the advantages side, well, for configuration fixed a priori, k-fold cross-validation gives you an unbiased estimate of the generalization risk with substantially lower variance than holdout through averaging. But there are three disadvantages. First, the cost. K model fits are needed instead of only one. Second, k implicitly also determines the training size, so choosing k is not just a computational decision. And third, and more subtly, the k training sets overlap heavily, introducing correlation between fold estimates. This limits the variance reduction achieved by averaging and means that the k estimates cannot be treated as independent, which matters when applying statistical tests, for example. The one exception is two-fold cross-validation, where the two training sets are fully complementary and share no data at all. Monte Carlo cross-validation, also called repeated random subsampling, takes a different approach. Instead of partitioning the data into folds, we repeatedly draw random train test splits, each time independently sampling a training set of fixed size n and using the remainder as the test set. We induce a model on each training set, evaluate on the corresponding test set, and average across these R repetitions. The key advantage over k-fold cross-validation is that the training set size n is chosen directly and independently of the number of repetitions R. This decoupling is useful when you have a specific target sample size in mind and want to control it precisely. The disadvantages are that there is no guarantee every data point appears in at least one of the test sets. Some points may never be tested, and that the splits can overlap, which introduces correlation between repetitions. Let us bring this together with practical guidance. As a rule of thumb, for very large datasets, holdout is appropriate. The test set is large enough that variance is not a concern. For medium-sized datasets, 5 to 10-fold cross-validation is the standard choice. For small datasets, MCCV or repeated k-fold cross-validation are preferable as they squeeze the most out of limited data. Now, three common pitfalls. The first is tuning on task. Anytime dtask is used to make a model decision, whether that is tuning a hyperparameter, choosing between architectures, or even deciding how to preprocess the data, the test set is no longer a clean estimate of generalization performance. The estimated risk will be optimistically biased because we have effectively searched for configuration that performs well on that specific test set. This is the most serious pitfall and the one that motivates nested evaluation, which we will cover in a later section. For this, also note that we always assumed in this section that we have a fixed configuration lambda producing a specific model given the data, basically. The second pitfall is reporting the best fold instead of the mean. The best fold is a biased maximum over k noisy estimates. Always report the mean. The third pitfall is treating evaluation as deterministic. This one is subtle but important. The estimated generalization risk is a random variable. It depends on the random draw of the split and if the inducer itself is stochastic. For example, in a neural network with random weight initialization or a random forest, it is also dependent on the random seed of training. Rerunning the exact same experiment with a different seed will also in general give a different number. A conclusion drawn from a single run without any quantification of this uncertainty is therefore unreliable. Let us close with the key takeaways of this section. The estimate is the expected generalization risk of the inducer at a fixed training size n. Both the configuration and the sample size are part of the definition. Any finite data estimator of this quantity has bias and variance. The choice of validation scheme is fundamentally a trade-off between the two, mediated by computational budget. Holdout is fast but high variance. K-fold cross-validation reduces variance through averaging at the cost of K-model fits. MCCV decouples the training size from the number of repetitions, which is useful when the target sample size matters. Never use the test data for any model decisions. This is the single most consequential rule in this section, and it will reappear in the nested evaluation section when we think about how AutoML systems must be evaluated. Finally, generalization estimates are random variables. A single run without uncertainty quantification is not a reliable basis for drawing any conclusions.